Okay, so today we're going to be talking about solving exponential equations and solving logarithmic equations. But the way I formatted this PowerPoint is it's broken up into those two pieces. So we're going to start off with kind of a laundry list of things to do here for exponential equations. The first thing that I want to do is review the conversions between exponential and logarithmic equations because it's been a few days since our last class period and a few days since we last practiced with some of this stuff. So if we need to dust off some of those cobwebs, I think it's going to be a good start to review some ideas there. Um, but that conversion principle, being able to take an exponential equation and convert it to a logarithmic equation, is going to be so valuable for solving these equations. And what I mean by that is it's going to make these equations a lot easier to work with. If you're still struggling with converting exponentials to logarithms or vice versa, then this is going to give you a lot of frustration. It's going to be a little bit challenging. But hopefully, you guys remember this principle that when we have something that's written as b raised to the x power equals y, that's an exponential form, right? An exponential equation. And we are able, if we have an exponential equation, to convert that to a logarithm by simply writing log base b and then opening up some parentheses and put our equal sign. Because exponential functions and logarithmic functions are inverses of each other, if we simply switch the position of the x and the y values here, then that's how we can figure out what goes in the parentheses and what goes in on the other side of the equal sign, because we should have log base b now of y is equal to x. So I like to think about this as the logarithm, once you have it set up, should be spitting out on the other side of the equal sign your exponent. Okay. Does anybody have any questions about that idea, or does this feel familiar?
This feels familiar.
Okay, good. All right. Well, if that feels familiar, then we're going to jump right into our first equation. And the way I broke this down, I hope, in my head, this is broken down into equations based on their difficulty level. So we're going to start off with the easiest exponential equation here. And we're going to do most of these on pencil and paper, just so that I can write some additional notes and so that you guys can see what it looks like on the page. So you can think about like, okay, I need to emulate what Mr. Aguilar is doing. I need to organize myself in this way because it's going to help me not confuse myself as I write a bunch of stuff down on paper. Okay. So this equation says 7 to the x power equals 343. Okay. You want to get used to saying that correctly. 7 to the x power equals 343. Okay. Because if you are reading this and you're saying to yourself 7x equals 343, it is not 7x. This is an exponential equation, exponential function. So we have to say that x power, because if we had the equation that said 7x equals 343, that would be a completely different problem. In fact, that would be a much easier problem because you guys know with this would be a linear equation. All you have to do is divide by 7, okay? But if you don't recognize that this x is technically the exponent, you do not divide to cancel out the base of an exponent. We've never done that before. So even though these look kind of similar, you have to recognize that the notation is different, which means that we have to handle it differently. Okay, so let's go ahead and switch over to pencil and paper to see how we're going to work this out. And I'll write some notes or some annotations as we go through this problem. Okay, so 7x, sorry, I did it there, right? Easy to do. 7 to the x power is equal to 343, right? This is what we call in the business an exponential equation. And the reason that we can identify this as an exponential equation is because we have something that looks like b to the x power is equal to y. Now, I don't want you to take this literally. This is just the form that the equation takes. So the base b here is going to change from problem to problem. The exponent or the variable may change from problem to problem, and then this number that represents the y is going to change from problem to problem. But you have to recognize, the different parts of the equation. So if I asked you, if we're looking at this equation, can you tell me what the base is here?
7.
7, right? What is the exponent on that base?
3. Oh,
Oh, are you sort of solving it in your head already?
I'm sorry. The exponent is x power.
It's just the x power, right? That's our exponent there. So I'm just going to sort of label these things just so that we get used to that, right? I'm trying to ease us into it. This is the exponent. And then this is, you could think of it as the y value or the output, and sometimes we call it the argument, right? And I just want to get down sort of the anatomy of these equations, so you know what you're looking at. Because it does you no good if you're a doctor or a surgeon and you have no idea what the different parts of the human body are, but you're just going in and cutting open whatever body is on the surgery table, right? So that would be a very scary thing indeed. Okay, so we need to know what we're working with here. I'm going to rewrite the equation just so I don't have all this like these notes over here. And as we start to solve it, the first thing that you want to do is make sure that we isolate the exponential expression. And what I mean by that is that whatever we have like b to the x power, that needs to be by itself on one side of the equal sign. Okay. So, at a certain point in this class, I've said, okay, you need to isolate this thing, make sure it's alone on one side of the equation, but maybe sometimes we lose track of what does that mean again. Remember, your equation has two sides. It's the left side of the equal sign. Sometimes I call it the left-hand side, and then the right side of the equal sign. Okay. So over here, we have the exponential part, b to the x, 7 to the x power. Okay. And then we just have some number over here, some constant. We could call it the argument if we wanted to, okay? The first tool that we're going to use to solve exponential equations is just convert the equation to logarithmic form. Okay. So what that means is if you have b to the x power equals y, you should be able to convert this. And this is just a little arrow, right? To log base b of y equals x, where you swap the position of the x and the y and write log base b, whatever the base is. So if I wanted to take this equation then and convert it to log form, what is the base of the logarithm going to be?
7.
7. Okay. So we're going to write log base 7, open some parentheses, put our equal sign, and then what goes inside the parentheses, what goes on the other side of the equal sign?
343 goes in the parentheses and x goes on the other side of the equal sign.
That's perfect. Okay. Any questions, comments there? I'm going to give you guys a moment for those of you that are still writing some stuff down. Any comments at all before I move on to the next step? Okay. Well, I'm hoping that you guys are able to recognize that throughout this semester, throughout this course, whenever we've said that we're trying to solve an equation, what we're doing is trying to figure out what number is supposed to take the place of the variable x, right? Find the missing value, in other words. And so when we started this equation off, we had this 7 to the x power, but I like to think about these exponents as they're trapped up there, kind of like a princess, a damsel in distress in the highest castle and the tallest tower, if you guys get that Shrek reference. Um, but we cannot interact with that exponent unless we can bring that exponent out from being an exponent. And so converting to log form is the way that we do that. So when we convert it to log form, we write log base b, which happens to be a 7 here. And then we swap the position of the x and the y, whatever those x and y values are. Okay. But now this x is now a free from the prison, if you want to think about it like that. Okay. And when we're solving equations in that sense, all we're trying to do is get x is equal to some number. Okay? So if I have a logarithm, log base 7 of 343, this is something that you can just evaluate in the calculator because there's no variable part on this left-hand side of our equation. Log base 7 is just a button in the calculator. 343 is just a number that we can put in the calculator. So what we can do is just take our finger and press math, go up twice to find the log base button, and then we can enter log base 7, 343, and then I get 3. So even though this thing looks intimidating, log base 7 to 343, it turns out that that's just the number 3. Okay, so all of this just becomes the number 3 is equal to x. And so we know what x is equal to. It's just equal to 3, which is something that I think Corey sort of blurted out earlier, because this was an easy equation. And maybe if you just did some guessing at the very beginning, you probably could have stumbled into the answer there. Okay. For some of the equations we're going to get into, they're not so easy where you can just look at the equation and sort of like make some guesses, maybe using your calculator to figure out what x is going to be. We're going to need to go through this process sort of systematically. So I'm going to put
Yes.
here for step 3, we want to solve the equation, whatever equation we might end up getting. But sometimes when we solve that, when we make the conversion from exponential form to log form, the equation's already solved. So it's really just one step, make that conversion, and you have your solution. So solve the equation and evaluate logs if possible. Any questions, comments, concerns? Okay. So in Alex, our solution set is just going to be 3. Okay, and let me plug in my power cord just so I don't die on you guys mid lecture. Any questions, comments before we move on to the next example? Still writing this. Okay, let's move on to the next one. Okay, and like I said, I'm going to be sort of going off of the PowerPoint. So I do work out that in the PowerPoint and try to give a little bit of commentary. But for the most part, I think this is going to be useful to just stay on paper so that we are not having to switch back and forth between the two media. So this is going to be equation number 2. We're going to solve the exponential equation. And the equation is going to look like 7 raised to the negative 2x plus 5 power is equal to, yeah, let me go ahead and unblur that.
Thank
You got it. So 7 is equal to the negative 2x plus 5 power, and that's equal to 1 over 2,401. I'm going to write all my notes over here in this side of the page. But remember that with these exponential equations, the first thing that we want to do is isolate the exponential term. So you should be able to tell me how many terms are in this equation. Can you guys does anybody want to venture a guess how many terms are in this equation?
One, two. I'm gonna say three.
Why are we saying three? Where are you thinking that?
2x, then 5, and then the 24, 1.
I see, I see.
My guess is
Well,
2.
Yeah, so the correct answer here is 2. So even though this is kind of a hefty expression over here, this is one thing, right? It's b to the x power, some base raised to some power. So think about this exponent, even though it's kind of a hefty thing, and maybe we have some terms within the exponent, that exponent belongs to the base 7. So together,
okay,
that's one term.
one term. Okay.
Yeah. And then this fraction, 1 over 2401, that's going to be our second term. Okay. So what we want to make sure that we do is every time we start off one of these problems, the b to the x power, whatever it is, however complicated that exponent looks, we want to make sure that that term that has the exponent is by itself. Okay. Now, is that the case starting off this problem?
No.
Yeah. Okay. So if that's the case, then really we're done with step one. We didn't have to do anything to isolate the expression here. But if I had like 7 to the negative 2x plus 5 power plus a number, then I'm going to have to like subtract that number over to the other side or maybe add a number to the other side. And we'll see an example like that shortly. But make sure that this guy is isolated before we start. Then the next step is the same step as the last problem. So if you have something that's in exponential form, we want to convert that over to log form. Okay. So this is just an arrow just to say that we're converting from this guy to this guy. And if you need that little formula again by your side, just so that it can help you visually to make that conversion, then please have that formula by you. But we're trying to get now log base b of y is equal to x. Okay. So when we look at the equation that we have, we don't have just an x and a y here. Really, those are representing pieces of this puzzle, right? So what is the base in this equation?
7.
7. Just like the last one, right? So we're just going to go down here, give ourselves a little bit of room to breathe. And when we convert this to log form, we're going to write log base 7, open up some parentheses, equals blank. Okay, so that is us converting this to log form. Okay, now what's playing the role of the exponent here?
The negative 2x plus 5.
Yeah. And so usually I'm just going to throw that on the opposite side of the equal sign. So now I'm going to put this negative 2x plus 5 over here. And then this guy, whatever is over here, it doesn't matter if this is a fraction, it doesn't matter if it's like a weird looking thing or an expression, a polynomial. I'm now going to switch that and put it inside of my logarithm. So this is going to be 1 over 2401. Okay, so now I should have log base 7 of 1 over 2401 equals negative 2x plus 5. Any questions, comments about that step? Okay. So now the next thing that we really want to do is if we have any logarithms in here that we can evaluate, let's just evaluate and simplify logarithms in the calculator if we can. So I'm going to evaluate any logs in the calculator, because this guy, if I just put it in the calculator, is going to turn into something really nice. And it doesn't look very nice right now. But again, if we take our time and we just put math, go up twice to get our log base function, we can input a log of base 7. And then inside the log, we're going to put a fraction. So I'm going to hit alpha y equals 1 over 2401 and then hit enter. And I get the number -4. So this logarithm, log base 7 of 1 over 2401, that's just -4. So like we're not going to write it as this scary looking logarithm anymore. We're going to write this as -4 is equal to -2x plus 5. Questions, comments up to that point? Okay, I'm trying to take a little bit of bigger pauses here to give you guys time to sort of write down these problems and also some time to think about it. But I really want to make sure, like, if you have any questions, if you have anything that you want to ask here, now's the time to do it, as opposed to waiting until it's, past 10 o'clock and I'm in bed sleeping like a baby, and there's nobody there to sort of help you answer any of these questions that you might have. Okay. So, do we understand what's going on here? Do we have any questions or comments? Anything at all? Okay. So I'm hoping that if you guys are good here, this should feel very familiar because I'm literally going through the exact same steps that I did on the last problem up to this point, where I made sure that my exponential expression was isolated. Then I made that conversion to log form. Okay. If it's not isolated and you jump the gun to converting to log form, you're never going to get to the right answer. Okay. So we need to make sure that we're following these steps every single time, and you need to approach these equations like they're a cookbook. So we isolated our exponential expression, the thing with the exponent, no matter how complicated that was. Once that was isolated, we converted to log form, right? Then if we have any logarithms, like log base 7 of this weird looking fraction, if we can put it into the calculator and get something nice and clean, then we want to do that, okay? Because now, once you get to this point, you're going to be solving either a linear equation, a quadratic equation, or in some cases, you might even have a rational equation. But we're being transported back to material from test 1 or test 2 or even test 3. Okay. So can anybody tell me by looking at what we have here, ignoring all this logarithm stuff because we're not worrying about that anymore, what kind of an equation is this?
Quadratic.
It is not quadratic.
It's
It's
linear.
not linear.
Not. It is a linear equation. Remember, the difference between a quadratic and a linear is a linear just has an x. A quadratic will always have an x squared. Okay? So that's how I know that this is a linear equation. And so when we're solving a linear equation, all we need to do is get the x by itself. So this next step is just going to be to solve whatever equation we end up with. In this case, it's going to be linear because we have just an x. And so we want to get that x by itself. So I need to do a little bit of work to get the x by itself. So if I asked you guys, let's go ahead and move this +5 to the other side. How do I move this +5 over? Yes, that's exactly right. Subtract 5 from both sides so that we can cancel out that 5. -4 minus 5 is going to be -9. This is now equal to -2x. And then finally, what do I do to cancel out this -2 that's next to the x?
Divide by -2.
Divide by -2 on both sides. The -2's cancel out. Since -2 divided by -2 is 1, we have just 1x left over. Okay. And then a negative divided by a negative is going to be positive. But if you don't like looking at fractions like that, then I urge you, just put this into the calculator. -9 over -2, and let the calculator do that work for you. It's just 9 over 2, so I'm going to leave it as positive 9 over 2. And that's it, because we're just trying to get x by itself, okay? And we have x is equal to some number. So that means our solution set must be 9 over 2. Any questions, comments, concerns? Okay. Now, what I recommend here, this is a recommended fifth step, is to check your solution. So if our solution is 9 over 2, what we're saying is that if I take the original equation and I plug in that 9 over 2 and replace the x, then I should be able to write 7 to the power -2 times 9 over 2 plus 5. That's the whole thing in the exponent. That when I put that in the calculator, that should equal 1 over 2,401. But I don't know that for certain because you may have made a mistake, right? And so this is something that you can do with any equation that we've solved before, where you plug in your solution, your proposed solution, what you think is the answer, back into the original equation to see if it works. So I'm going to grab my calculator here, and I'm going to put 7 raised to the power -2 parentheses. I'm going to put a fraction in the parentheses, 9 over 2 plus 5. And I'm going to see if that equals the same thing as 1 over 2401. So I'm getting this weird number, and that's okay. Let me just put in my calculator a fraction, 1 over 2401. I think this is going to spit out a fraction again, so maybe we want to nix that one. But what we could do is 1 divided by 2401, because this is definitely going to give me a decimal, and it gives me the exact same decimal. Okay, so that means that these two sides of the equal sign are equal to each other, and since these are the same according to the calculator, that means that our solution is valid. Okay, so we can go ahead and go back over here and say, in Alex, our solution set will simply be 9 over 2. Questions, comments, concerns? Okay, again, giving an awkward pause there to make sure you guys have time to write this stuff down. And last call for questions on this one before we move on to the third, slightly more difficult problem here. Okay. Well, now I do want to kind of take us back to the PowerPoint momentarily. And what I want you guys to know is that if you're downloading these PowerPoints and viewing them with the slideshow in either Google Sheets or Microsoft PowerPoint, if you happen to have it, then you should be seeing these animations where I run through the problem. So the process is the same, right? This is just a recap of what we just did here. We converted our exponential equation to logarithmic form, and then we evaluated our logarithm so that we got -4 instead of this scary looking number, okay? So once we have that, we're back to a linear equation. And so at that point, you're either going to be looking back at a linear equation or a quadratic equation. In some cases, it's going to be a rational equation, but we'll cross that bridge when we get there. In any case, you're just trying to use the rules that you had before to get the x by itself. So with linear equations, that's really simple because we just need to move some stuff over. And I usually like to move my variables to the left and my constants to the right. But here I just thought it would be easy to just move our constant 5. We subtracted that over to the left to get the -9. And then we could just divide by the -2, which is what we did to get our final answer, 9/2. Okay. You can check your solution by plugging it back into the original equation, but then we're off to our next discussion. All right. So in ALEKS, you're going to start seeing some problems that say solve this exponential equation. And a lot of the times converting that equation to a logarithmic form into a log expression is going to make that easier to solve. Unfortunately, sometimes when we evaluate log expressions in the calculator, they're not going to turn into nice and neat, pretty whole numbers. Okay. So in the last two examples, when we evaluated something in the calculator just to simplify the equation, we ended up with something like -4, or in the first example, we ended up with just the number 3. Nice whole numbers, nothing too scary looking. Okay. But sometimes when you evaluate something in the calculator that's a logarithm, you're going to get an irrational number, something that cannot be written as a whole number or a fraction. Okay. So for problems like this, we're going to be expected, and ALEKS is going to ask you to give your solution in exact form and then give the solution in its approximate form, rounded to 3 or 4 decimal places. Okay, so you need to read those instructions very carefully because if you just dive right in without reading those instructions, you're going to be missing some crucial piece of information. Corey, did you have a question or a comment there?
No, I just comment out you 4 decimal.
Yeah, yeah. So those homework assignments, definitely they say that you need to round to 4 decimal places, but watch out for those instructions. Make sure you're reading them carefully. Okay, so the next problem that we're going to solve here is 5 to the x power is equal to 102. Okay, let's switch back over to the document camera to do that one. Okay, so I'm going to keep on annotating over here. First step, so we want to isolate the exponential, so b to the x power or whatever to whatever power, okay? Is that isolated? Are we done with step 1?
Yes.
Yes, okay. I was like, definitely not a rhetorical question. But yeah, if you were waiting just to make sure that other people had a chance to answer, make sure that that's clear to you that we have the 5 to the x power by itself. Okay. So then the next step we're going to be looking to do is just convert to log form, which is where you might want to get that formula to sort of guide you. B to the x power equals y gets transformed to log base b of y equals x. Okay, so I'll go back over here and draw my little arrow to say that this should now be log base 5 of 102 is equal to x. And that's really nice now that I've made that conversion because the x is by itself, right? So I'm just going to write over here. We're getting this in log form. Any questions, comments, concerns? Because I'm picking up speed a little bit here, so hopefully I'm not going to lose anybody. Literally following the same steps we did before. Okay. Now, previously, I said, well, if I have log base 5 of 102, and these are just some numbers, I can go ahead and plug that into the calculator to simplify. So let's go ahead and do that. We'll hit math, go up twice. Log base 5 of 102. And I get this god-awful number, 2.8736 you might say to yourself, if you're in a rush, well, that's like 2.87. I'm just going to put 2.87 in Alex and see if it takes it. And then it's not going to take it. Okay. So this, when you try to evaluate, is an irrational number. And what that means is that it cannot be written as a whole number or a fraction. So it's like pi, right? Where we can't write all of the digits of pi. As soon as we round pi to 3.14, you've actually changed its value. You cut off some of the value that were in those extending digits or decimal places, okay? So as soon as you cut off this number, 2.873657, and you cut any of those numbers out, you've changed your answer, okay? So if Alex asks you, what is the exact solution for this problem? And remember, the solution is always of the form x is equal to something. Then what Alex is expecting you to type in for your exact solution is these braces. And literally, we're just going to leave this as log base 5 of 102. Okay? So, and then I will make a little note over here that log base 5 parentheses 102 is how I've gotten you guys used to writing these down. But I'm sure you've seen in Alex that they are going to start writing these as log base 5 and then 102 where they don't show the parentheses, but they're implying that there are parentheses there. Okay. So this I'm going to label as implied parentheses. And just to let you guys know what my feelings are about this implied parentheses business. I think it's fine if you're like very comfortable and you've been working with logarithmic equations for a very long time. But like most students, whether we're in a summer class or a regular spring or fall semester, like you don't work with these long enough to know that those of us that are experts imply that there are parentheses right here. Okay. So what I would say is that Alex is going to accept it with the parentheses. Sometimes it doesn't let you put the parentheses, so you're just going to have to get used to this idea. But when you're writing stuff down on paper, I highly recommend that you just keep those parentheses because remember, this is a log function, and the stuff in the parentheses is the input of that function. So I think when you lose the parentheses, you're starting to lose some of the facts about what we're dealing with here. Okay, and then also sometimes students think that this is now log 5 to the 102 power, and that's not what we're writing here. We're saying that this is the log base 5 function, and that log base 5 function is taking an input of 102. Okay, so this is not a base number, and this is not the exponent in terms of like an exponential expression. This is a log base, and then this is the input of that log function. Okay. Now, at the same time, I kind of feel like maybe I'm preaching to, not preaching to the choir. What is the opposite of preaching to a choir? Maybe it's falling on deaf ears. Maybe it's lost on you because it doesn't make that big a difference as far as like you guys trying to get through these problems and get through the test, right?
I
So,
have a question.
yeah, go
So
ahead.
for the implied parentheses, is it for the 5?
No, the implied parentheses are right here
For the 102?
for the 102,
Okay.
but we don't show them, right? And so like this whole rant that I'm going on here is just to say that like throughout this semester, I've been saying, oh, if I have an x, there's an implied 1 in front of it. Or if I have an x squared and there's not a number in front of it, there's an implied 1, right? If I have a variable and there's no exponent, well, that's an implied 1, right? And that got, for people that are new to this, it feels really frustrating for people to tell you that there's something there that you can't see, right? So I'm trying to level with you guys that that can be very frustrating, but you do need to watch out for it because Alex was built by mathematicians and engineers that have designed it in a certain way. And so it looks one way on the computer and it looks different on paper the way I'm writing it down. Okay, so understand that these are the same thing, whether you put the parentheses around the 102 or not. I think I pointed to those incorrectly. Whether you put the parentheses on the 102 or not. Okay. So that's one thing that you have to watch out for. The other thing is that Alex is going to start having a button where it says, oh, click on this button to put your exact solution. Okay. And then it's going to say x is approximately equal, and they're going to use this like squiggly equal sign. That means approximately equal. And you guys have probably seen me use it here and there.
Mhm.
And then it's going to have a box here where you have to put the exact solution and then you need to put the approximate solution here. And Alex is also going to say write this approximation to 4 decimal places. So I'm going to just plug this into the calculator. And then I'm going to grab 4 decimal places, right? 2.1234. So I'm going to put this as 2.873, and then that 6 needs to round up because this neighbor on the right is a 5. So that needs to round up to 7. Okay. So we want to round off to 4 decimal places. Okay, if you round that incorrectly, you might have done all the other work correctly, right? You might have done it right. But this class here, we haven't talked about rounding at all because that's something that's assumed that you know how to do from grade school, right? And that might not be true because we don't round all the time in our everyday life. Okay. Or sometimes we don't round the way we do in grade school in everyday life. Usually when I'm at the grocery store, I'm just like rounding up to the nearest dollar. But back when I didn't have as much money, I was definitely rounding up probably to the nearest 10 cents. Okay. But we want to round off to the 4th decimal place there. Okay. So these two numbers represent the same thing, the exact solution versus the approximate solution. And so Alex is going to start asking you for both. Okay. Questions, comments there. I know that was kind of a long-winded discussion about that. We're going to have another equation here in a second so we can see how this exact and approximate solution works. But questions, comments? Okay. You guys ready for the next equation? Okay. This is going to be the last exponential equation here. Because I hope that you guys have noticed that there's a pattern that if you go through the steps of this cookbook that I'm kind of giving you guys, that it should be just follow the recipe, follow the steps every single time. So this one is going to be our last one. I'm going to call this difficulty level 3. And it's going to be similar to what you guys see in Alex. So let's say we have 1,362 is equal to 19 to the t power plus 6. And we need to solve this equation. So this is a t power here. I'll zoom in so we can see this a little bit better. Okay. Solve the equation. Okay, and just let me know when you guys are ready. You can go ahead and type ready in the chat, or you can unmute yourself and tell me that you're ready.
Ready.
Muted.
All right. Look at the last ones we just did. What was the first thing that we have to do whenever we solve one of these exponential equations?
Isolate the B.
Yeah, we want to isolate the exponential part, the b to the x power. Okay, so we have 1, 2, 3 terms in this equation. Which one is the first, second, or third? Which one is the exponential expression or exponential term?
Second.
The second one, right? So this is the guy that I want to get by itself. Okay. So what is over here sort of crowding out this exponential expression? What do we have over here that we need to get rid of?
Six.
The 6. Okay. So let's get rid of the 6 by moving it over to the other side of the equation, right? We're going to be regular old Donald Trumps over here. We can't have any of these guys. We need to deport them over here to the other side of the equation, right? Okay. Hopefully that didn't strike a nerve with anybody. Um, so we're going to go ahead and deport this -6 over to the other side here. Okay. And then -6 divided by -6. I'm sorry, I'm all over the place, right? 6 minus 6 is just 0, so we can cancel that out. And then this number, even though it's like 1,362, and you might say to yourself, sir, we've never had a big number like this before. It's just a number, okay? We're going to do the same thing that we've done before. We're going to take our calculator, 1362, we're going to subtract 6.
1356.
Now we have 1356, okay? So I'm going to put 1356 down, equals 19 to the t power. Are you guys okay with this?
Yes.
Okay. So now this is just a note on style or personal preference. Okay. If we look at this equation, we have the b to the x power part, the exponential part, on the right-hand side. And for all of the previous equations, we had it on the left-hand side. Okay. So I know that when you guys are working out problems or when you're watching your teachers work out problems, that when they start moving things and they're like, oh, you usually put this on this side and now you're doing it on the other side, that's confusing. Okay. If you don't like this exponential part on the right-hand side, then just rearrange this so that it's 19 to the t power equals 1356. You can rearrange this and it doesn't change anything, okay? So we're just sort of flipping the sides of the equal sign. We've done this the same with quadratics in the past. So you can rearrange if you prefer to put it in the correct order, in the order that we're more comfortable with, okay? But then we're just going to convert to logarithmic form, right? Because we have as an exponential. So if I need to write this in log form, what am I going to write down?
Log base 19.
Log base 19, parentheses equal.
Okay.
What goes in the parentheses?
1356.
1356 goes in there. And then what goes over here on the equal sign?
T.
T, right? Because we're just taking these guys and swapping where they were in the original equation, right? Questions, comments about that step? Okay. Well, now we have the t isolated, right? So that means that t, our variable that we're trying to solve for, is equal to this number. And so what I'm going to do is just check to see if we can evaluate this in the calculator, and it gives us a nice pretty number. I'm going to put log base 19 of 1356 in there, hit enter, and I get this god-awful decimal number, 2.449463045. Okay. If that doesn't come out to a nice whole number, then we want to say, 1, we're done, we have our solution. Okay. So right here, I'm just going to say evaluate the log if possible. And here we got a really ugly irrational number. And so the way Alex is going to want this is it's going to say, here's a bubble that says there's no solution. Or the exact solution
Mhm.
is blank. okay? And then it'll have t is approximately equal to blank. So what you're going to have to do here is understand either this problem has no solution or it has an exact solution. But what we found is that this has an exact solution because we have t is equal to this thing, right? So this is our exact solution. So I'm going to say, yep, we have an exact solution. And it is just log base 19 of 1356, close the parentheses there, and then close the brackets. I didn't give myself enough space. That was my bad. Hopefully you guys understand that. Then I'm going to go back to what I put in my calculator, log base 19 of this god-awful large number. And I'm going to round this off to 4 decimal places. So it's going to be 2.4495. Okay. 4495. Again, really apologize for not making these boxes bigger. I'll do better next time, I promise. Okay. So now we have our exact solution, which is a logarithmic expression, and then we have our approximate solution here, which is rounded to 4 decimal places. Questions, comments? Okay. There is one more thing that you have to watch out for because if you weren't frustrated enough with Alex, then there's one more thing to be frustrated about. Okay. So when you read the instructions in Alex, sometimes it's going to say something like, write the solution in terms of the common or natural log. Somewhere in the instructions, it will say something like that. Okay. So this kind of is a little bit annoying to me because Alex is a online homework platform and it should understand that like you guys have these fancy calculators, the TI-84 or possibly a TI-84 CE plus. Okay. So what Alex is looking for is if we get our solution, which we just got, as log base 19 of 1356, right? Back in the day, basic calculators only had the common log button and the natural log button. Only these two buttons were available. They didn't have the option to press math and then change the base of these different logarithms. So instead, what people used to do is apply this thing that's called the change of base formula. I'm going to put change of base. Okay. And the way you express this solution, the way Alex wants, is you're going to put this as a fraction. And I'm just going to use the common log so that we don't have to worry about doing this multiple ways. Okay. So the common log, remember, is just log where we don't write the base. So I'm going to put log of something over log of something else. Okay. The 1356 is going to go in the top common log, 1356. Okay. Then the base of our original answer, the way you guys have sort of worked it out, that's going to go in the log in the bottom. So the way Alex wants to see your exact answer is as this fraction. So this is our exact solution. but written in terms of the common log. Okay. So if you're sitting there frustrated and you've solved this problem and you got your solution looking something like this and you type it in like this, and Alex is saying like, oh, wait a minute, you actually did not get this one correct. And you're certain that you've gotten that correct. Then you need to go to Math World and ask the tutor or go to Math World and ask me, like, sir, what's going on here? I think I'm doing this right, but it keeps telling me that I'm wrong. What you don't want to do is like assume that you're wrong and then start messing around with the formula, right? Because I'm giving you the recipe that you need to follow to the T, okay? And if you start changing that recipe, I don't know if any of you guys have ever baked bread, but it's a very delicate process. If you don't have the right amount of yeast or the right amount of sugar, or if you don't knead the dough the right amount of times, right? Or let it ferment for the right amount of hours, like you're not going to get the product or the end result that you want, okay? You need to follow the instructions, the directions that I've given you here, and trust that you're doing it correctly, okay? If I could go back in time and design Alex myself, I would say, yeah, go ahead and take this. This is fine, okay? But we just need to go one step further and change the base so that we're writing our answers in accordance with what Alex wants. So everything needs to be in terms of the common log, and it should look like this. Okay? And that's going to be the last thing I'm going to say about these exponential equations, because we're going to be moving on to logarithmic equations. So does anybody have any questions before we leave these sort of in the dust? Okay. Well, we're not really leaving it in the dust, right? We're just leaving it in the dust for now because I'm sure that you guys are going to definitely go to Math World and ask for help when you guys get stuck, okay? We're definitely not going to try to invent our own math and try to mess with the formula here. We're definitely not going to do that, okay? But if you need to, you can go back through the PowerPoint and I run through these exact steps here. I sort of skip a little bit of the work there in between. So you will have to fill in the blanks a little bit. But now we're moving on to the second half of our lecture here. We're going to start solving logarithmic equation. Okay. All right. Okay. So for these logarithmic equations, if it feels like it's really overwhelming, hopefully I'm going to be able to categorize these logarithmic equations into like some simple categories here. And as I go through this, maybe I'll sum up as best I can how to approach these log equations. Okay, so this looks like a long laundry list. We're going to ignore this a little bit here and just go right into our first equation. Okay, but before we do that, you have to remember, before we started all of this jazz, started talking about module 4 and started talking about one-to-one functions and inverse functions, remember that exponential functions are one-to-one functions. They have an inverse or an opposite function, something that will reverse or undo, cancel out those equations, and those are logarithms. Okay, so logarithms and exponentials are inverses of each other. They are both one-to-one functions. And because they're both one-to-one functions, if you kind of vaguely recall when we introduced one-to-one functions, we had this weird looking definition where we said a function is one-to-one if f of a is equal to f of b, then that implies that a is equal to b. Okay? The reason why this is going to be a useful property here is because anytime we have a function that is one-to-one and we have an equation, so this equal sign, right? If I have that function on both sides of the equal sign, so I have the function f here and the function f here, and we know that f is one-to-one, I can just say, oh, let me just drop those functions and just work with the interior, the stuff that was inside the parentheses. And you guys saw this for an example of an equation that we saw in one of the worksheets. You had something like the cube root of, I'm just going to make something up here. Let's go with 5x plus 4 is equal to the cube root of x minus 7. Right? Just making this up. It turns out that when you guys solved an equation like that, some of you guys just went in there and said, oh, I'm just going to drop the roots here and then just do 5x plus 4 equals x minus 7. And without knowing why you can do that, it turns out that this cube root function is a one-to-one function. So if I have it on one side of the equation and on the other side of the equation, then I can drop that complicated function and just work with the stuff that's on the inside in a simpler equation. Okay. We're going to see this play out for logarithms, and I assure you, it's going to make them seem so simple. Okay. So let's start off with our first one here. We have log base 2 of 2x plus 5 is equal to log base 2 of 6x minus 7. Okay. Ooh. I'm going to go ahead and switch back to pencil and paper so that we can solve the logarithmic equation. Can you guys tell me, how do I know that this is a logarithmic equation? Just take a wild guess. No wild guesses? Thanks, Billy. I knew somebody was out there listening to me. Right. Yeah, it's because we have logs here, right? Okay. So this new technique that we're going to use for solving these types of equations is if I have a log base 2 of, let's say, a. I don't know what that a is. It could be anything. It could be a single term. It could be an entire expression like a polynomial. And if that is equal to log base 2 of b, then the 1-to-1 property says if I have one logarithm function over here, and I have that exact same logarithm function over here, so log base 2 and log base 2, I have 1-to-1, then I'm allowed to drop the logs and then just work with the equation a is equal to b. So the first step here, if I acknowledge that I have log base 2 and log base 2 on both sides of the equation, and I have two logarithms, then the first step is going to be to apply the, not log function, the one-to-one property. And I'm going to abbreviate that eventually as the number 1-to-1, but one-to-one property, which in other words, we can think of this as just drop the logs. Okay, so I'm going to rewrite this equation just so we can see our original without anything written over it. You don't have to necessarily rewrite the equation, but I'm going to say cross out the log base 2, cross out the log base 2. And so I have 2x plus 5 is equal to 6x minus 7. And that's it. I applied the log property, or applied the 1-to-1 property. Questions, comments about applying that property? Does that seem like easy, or does that seem kind of weird? Okay.
Seems too easy.
Seems too easy, right?
Mhm.
And like that is gonna always be like a strange feeling, this suspicion that you guys have, because it's like, well, what do you want from me as the teacher here? Do you want me to make it harder than it is, or do you want it just to be easy? Have you ever been in a relationship with somebody who was like so good to you that you didn't trust them? and then you ruined it because you overcomplicated the relationship? Okay. Like that's what you're doing here. And so you need to trust here that the math, if we just listen to its needs, it's giving us everything that we need to see and nothing more. Okay. It's that easy. Okay. So now when we drop the logs here using the one-to-one property, then this is just a linear equation.
Hmm.
And so we just need to get x by itself. And so I'm going to sort of take the reins here and say, I like to have my x's on the left and move my numbers to the right. So if you don't prefer that, you can handle this however you want. But it's my video lecture. I'm going to go ahead and do subtract 5 from both sides to take care of the constant. So -5 and +5 cancel out. I get 2x is equal to 6x minus 12. I'm going to subtract the 6x
Six,
back
six.
over here to cancel out the 6x's. I'm now going to have -4x is equal to -12. And then finally, I will divide by -4 on both sides so that I have x is equal to +3. But like that linear equation stuff, all the way to the end, this is old news, right?
Hmm.
And so what I noticed after teaching this for a really long time is that as we get to the harder things, students start to make the older things, well, they forget some of the older things, and then they start overcomplicating the stuff that should be easy. Okay. Okay. Now, maybe the word easy and difficult isn't exactly what I want to do here, but like you need to make sure that you can solve these linear equations because kind of similar to when we were solving rational equations, the ones that had those big fraction terms. Once we canceled out the fractions, we got transported back to a linear equation or a quadratic equation, right? So I said you cannot forget how to solve a linear equation. You cannot forget how to solve a quadratic equation, okay? That same situation is happening here. We applied some new property, which is a fairly easy property to apply, I hope. Drop the logs and then just solve that equation. Any questions, comments? Okay. So here we just needed to apply the one-to-one property, and then really the second step was to solve the remaining equation. Okay, last questions, comments, concerns for this problem before we move on to the next one. Okay. The next one's going to be a little bit more difficult, okay? Are you all ready? Go ahead and put ready in the chat if you're ready, chat. Okay, let's say we have the natural log of x squared plus 3x is equal to the natural log of 10. Okay, I'm gonna make us some notes over here. Make us some notes. Just make us some notes. And I'm gonna zoom in. We're gonna solve that equation, right? Welcome to the new game show called Solve That Equation, where you have to solve equations. Um, okay. So this is a log equation, right?
Hmm.
And it doesn't matter if I have these natural logs, these ln's, or if I have a log base, whatever, right? I have logs on both sides. So clearly, if I have log base b of x is equal to, sorry, let's use a here, of a. I'm going to use a capital A here. And I have log base b of capital B. Hopefully that's not too confusing. Then if I have the same log bases, then I can drop the logs, right? And that's what we're calling our one-to-one property. What do you think the first step is here, guys?
Drop the natural logs.
Drop the natural logs, right? Just drop those natural logs, okay? So we're going to drop the natural logs. So all I have left over is x squared plus 3x is equal to 10. Okay, so we drop the logs. But keep in mind, we can only do this here because we have one log over here and one log over there. 1 to 1, right? If you don't have two logarithms, then you cannot drop the logs. You can only drop them when you have two logs. Okay? So keep that in mind. I'm being very extra here because it's very important. Once we get to the next equation that we're going to see, you're going to have some more logarithms, and then every semester, without fail, a student will just say, oh, I just dropped all the logs. Unless you have only two of them, you can't do that, okay? But for this one, we're good. Can you guys tell me, what kind of an equation is this?
Quadratic.
Mhm.
Yeah, that's a quadratic equation.
Mhm.
Okay, so in the interest of not losing anybody here, the next step is to solve the equation. It happens to be a quadratic, and so you guys need to get this into standard form, which remember that's ax squared plus bx plus c equals 0. So we're trying to get this equal to 0. So what do I need to do next?
Get the 10 to the other side.
Get to the 10 to the other side, right? We're going to subtract 10 from both sides so that now I have x squared plus 3x minus 10 equals 0. And then I can jump right into the AC method, okay? In the past couple of lectures, I started doing the fast method or the quick factoring method here, but I don't want to lose anybody. And I think that in my face-to-face class and maybe in this class, I'm starting to lose people when I start doing a fast factoring. So I'm going to do the full AC method here. I'm going to take 1 times negative 10 and look at all of the factors of negative 10, right? 1 times 10 is 10. 2 times 5 is 10. And then nothing else works. And I need a negative 10. So when I multiply these, one of these factors has to be negative, right? But I also need to choose the pair that's going to add or subtract to give me 3. So that has to be 2 and 5. And I need to have a negative 2 because negative 2 times 5 is going to give me the negative 10. And negative 2 times 5, I'm sorry, negative 2 plus 5 will give me a positive 3. Okay? So the long way is to rewrite this as x squared minus 2x
2x
plus
plus
5x
like that.
minus 10, and we're just going to kind of ignore the 0 for now. We look at these two terms here and ask ourselves, what do they have in common?
X.
They have an x in common. So we're going to factor out the x. And then you kind of have to reverse the distributive property, right? X times x will give you the x squared back, right? So x times x, that's what's going to work here. And then x times what gives you the negative 2x back? Well, we already have the x. We're missing the minus 2. Okay. We can then look at the next two terms and say, what do these guys have in common, or what divides into both of these? And that's going to be a positive 5. That's the biggest number that goes into both. Let me color coordinate this a little bit better. And then we need to have 5 times x to get 5x back, and 5 times negative 2 to get the negative 10 back, right? So
Mhm.
that means our factors are x minus 2 and x plus 5. Now we can use the zero product property to say this is going to be x minus 2 equals 0 and x plus 5 equals 0. And then by adding 2 here and here, we get x is equal to positive 2.
2.
We subtract 5 on both sides of this one, and we get x is equal to negative 5.
Mm-hmm.
So like again, The one-to-one property, which was literally the first line that we did here, is the only new stuff, right? You cannot be forgetting this old stuff from test 2, right? And from test 3. It's not going away. You cannot hide from it. So if you're still struggling with the AC method and factoring, then you need to make sure you're going to Math World. Go find your friendly neighborhood Pete or whichever is your preferred tutor, or really the tutor that's on the clock at whenever you log in. And like get them to help you practice that. Tell them like, hey, I'm having trouble with the AC method still. I know I should know this, blah, 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 negative self-talk, but can you please help a brother out, right? Like do what you need to do because like this isn't going away, at least not for the next 2 weeks, okay? After the 2 weeks is done, then it'll go away forever, right? But we need to get you through and across this finish line, okay? And we're so close, we don't want to drop the ball here, okay? Or as the kids say, you don't want to fumble the bag. Okay, we're so close. So any questions, comments about this? Did I lose anybody at any point? Do you want me to review anything here that we went through?
Yes, can you review where you said x squared minus 2x plus
Yeah,
5x minus 10?
this part.
Yes, so I always tend to skip that next part,
You skip this line that I'm pointing to or the next line?
the next one, where can you repeat the step in between that? Where you
Yeah,
under,
yeah.
so I was
So
writing it down.
what you're doing here is you're saying to yourself, what do these two terms have in common? So let me grab, a sheet of paper here so I can hide some stuff, right? Pretend that we're going back in time to this problem, right? Let me zoom in. When you're factoring by grouping at this point, you're looking at these first two terms and asking yourself what they have in common, right? So x squared and negative 2x, Gina, specifically, what do these guys have in common?
They have x.
They have an x. Are you okay with them being an x, or are you saying like they have an x in common because we did it already and and because you know that the answer is x?
No, I understand they both have x.
Okay, cool, cool, cool. So when we first introduced this idea, we factored out the GCF at the beginning, right? And then we opened up some parentheses. And then with these two terms that we had here, one way that we said that we could figure out what goes into parentheses is whatever that GCF is, we can divide it out of these two terms. So like if I had two x's, right? Because this is x squared, so technically it's x times x. And I canceled out one of the x's for this first term, well, then only one x will remain. So you could do that by dividing out your GCF, or you could do it by the way I usually do it, where I say to myself, x times what gives me back the x squared. And this is where maybe it gets lost on some students because I prefer checking the distributive property and checking by multiplying. Okay. But like that doesn't come easy. I have to do the work of multiplying to see what I need. Like I'm going to say x times something gives me negative 2x. And I need to know that that's going to be a negative 2. So if you don't like the multiplication method here, if I just divide out the GCF, if I said they had an x in common, and I have negative 2x divided by x, well then these x's are going to cancel out. So what's left over is just going to be this negative 2, which is the same thing I would have gotten if I did it my way.
Okay.
And then when you move over to the next two terms, you're doing the same game, but you're not going to find the same GCF. It should be a different GCF, right? So like for 5x and 10, here we might ask ourselves, what is the biggest number that divides into 5 and 10? And you got to think to yourself that that's going to be a 5, right? So I'm going to put a plus 5 here and then open up some parentheses, and that's the GCF here. And so if you want, you can say, let's divide this by 5 and divide this by 5 to see what we get. So if I have 5x divided by 5, the 5's cancel out, and what am I left with? Well, I'm going to be left with an x,
Negative.
right? And then negative 10 divided by 5 should be negative 2.
Okay. Thank you.
Yeah. So, I mentioned to you guys before, I think maybe a couple times throughout the semester, like if, once we pass a certain subject, I start to speed up, I start to skip some steps, but like if it's still like bugging you, then you are completely free to ask me, like, sir, can you kind of go through that and show all the steps here? Because like it's not clicking for me because you're not showing the steps. And when we have time to do that, I'd be happy to do it. But then, there have been other class periods where it's like, man, we just need to get up and go. We need to get through this material. And then, like, good luck in the homework, try your best, and then go to Math World. So I think right now, if we need to take our time, we'll take our time. Okay. So hopefully that makes sense of how we got these factors. And then this x minus 2 became your first factor, x plus 5 became the other factor, and then we use the zero product property, and hopefully that stuff is a bit easier. But I do notice that a lot of times students will get stuck from this step to this step. So don't feel bad if that's you. Just make sure, well, maybe, again, I was raised Catholic. I've told you guys this before. Feeling bad is not the worst thing in the world, because sometimes it motivates you to get help. But just make sure that you're actually going and getting that help and asking the questions, because if you're really self-conscious about like, oh man, I don't want to ask this question because people are going to think I'm dumb. Like, you want to pass this class, right? Like, you want to not waste your money by failing a class, then ask the question. Okay? Because I guarantee you that everybody in the class is living their own life. They're not concerned about the questions that you're asking. And even if they are annoyed with you asking too many questions, whatever that means, like, who cares? Like, they don't run your life. You need to get your help and get yours because nobody else is going to do it for you. Okay. So just make sure you're asking for help, and don't be scared to sort of put yourself out there. Okay. Let's look at another one just so that we have some more practice. Okay. Got a slightly easier equation coming our way. So this is going to be log base 2 of x is equal to 5. Okay. And I kind of want to compare and contrast this to the last one. So once you have that written down, okay. So compared to this problem, or compared to the last one, how is this problem different? I'm not looking for like very minute details. Like, it doesn't really matter that the log base is different, but like there's something specific that I'm looking for here, which is distinct from the last two examples. How is this one different?
There's only one log?
There's only one log. That's exactly what I was looking for. Thank you so much. Okay. There's only one log. Okay. So if you go into this thinking like, oh, I'm just going to do exactly the same thing I did last time. I'm going to drop the logs. You cannot do that here. So I'm going to put here caution.
And is that because the rule is you have to have two?
To apply the one-to-one property, you have to have one-to-one logarithms. But we only have one logarithm. We don't have another one logarithm. Does that make sense? So no dropping logs. Okay. So there's two flavors that we're seeing here of these logarithmic equations. The ones where we have two logs, the ones where we only have one log. Okay, and maybe, if I was a smarter man, I would have started us off with the equations that only have one log. Okay, because I think it makes sense. My OCD brain is yelling at me, has been yelling at me all day. It's like, okay, well, why didn't we just start with one log and then do two logs and then do three logs after that? That makes so much more sense. Okay. But I'm not going to beat myself up too much about that. I think you guys will be able to figure this out. When you have one log, your first step, as long as your logarithm is isolated and positive. So maybe I'll put my first step as isolate your log. Isolate the log base b of, I'm just going to put y here, whatever that is. So isolate the log expression, which it already is isolated. Okay, and then don't take this y too literally. Okay. The next thing you're going to do is just convert to exponential form. So this should feel really familiar, very similar to when we were solving exponential equations. You guys are probably sick of me referring to the 1980s classic, The Karate Kid, but like we had to convert things from exponentials to logarithms and back and forth, right? So we had our wax on, wax off. That's what we're doing here. So before we had exponential equations converting to logarithms, now we need log base b of y is equal to x, and we need to convert that back to the base b, the exponent is x, is equal to y, okay? And I'm glad that you guys are hearing the wax on, wax off when you're doing the homework. Okay. It's the silliness of it that sticks. And hopefully, like, when you're taking the test, you're going to remember these stupid little expressions that I keep using, and it's going to jog your memory. At least that's my hope. Okay. My real hope is that you guys wake up in a terrible cold sweat in the middle of the night because you're solving these equations in your brain while you're sleeping. Okay. Because then you're putting in enough work at that point. Okay. So to go to exponential form, what's the base of this logarithm?
2.
2.
2. I'm going to write 2. And then don't get too bogged down about this being a variable x and this being a variable y. We're going to take the x here and the 5 here. And remember, this 5 is our exponent. So I'm going to put 2 to the 5th power is equal to the stuff inside the log, which is x. So here we're trying to sort of break the stuff out of the logarithm. It's trapped inside the log function, inside the parentheses. And so by converting to exponential form, we can take the stuff out of this parentheses, which is what we're trying to get to, that x. And then the 2 to the 5th power, that's just an expression that you can put in your calculator. So this in the calculator should come out to 32, if I'm not mistaken. So just to prove this, 2 to the 5th power is 32. Okay. And you're done. That was it. For this equation, all we needed to do was convert to exponential form, and then evaluate the exponential expression here, 2 to the 5th power, and then just came out to 32. So this is going to be good. We're going to say our solution set contains the number 32. Questions, comments, concerns? That one seem easy enough? Or do you guys want this to be hard? Okay. So I kind of feel like these things look a lot more intimidating than they are, but once you get in there with that first step and process this a little bit, if the equations aren't becoming like an easier thing to look at, then maybe we're fumbling that first step. Okay, so just make sure you're going through these steps that I'm giving you. And then at that point, the equation should be familiar, like an old school equation, a linear or quadratic, okay? So one thing I'm going to say here as a note is that for these log equations, we need to check our solutions before we
Mm-hmm.
before we put our answers um into Alex. And I totally, let's see what's going on with my document camera. Let's see if we lost our connection here. You guys can hear me rambling, right?
Yes, like a
Yes.
madman.
Like a madman. All right, here we go. Let's turn that light back on. Okay. So you need to check these solutions, and we're going to check them the same way for these log equations that we have in the past. So I'm going to write down log base 2 of x, except we're going to check to see if 32 does work. So I'm going to put 32 into that function. And then I'm just checking, so I'm going to put a little question mark here because I don't know for sure. But if this equals 5, then we should be good. Remember, all we need to do is evaluate this in the calculator, and if we get a true statement, like 5 equals 5, then we should be good. Well, sure enough, math, go to log base, put log base 2 of 32, and I get 5. So I have 5 equals 5, which is true, which means that I don't have to worry about this solution. This is correct. Okay. So remember to check your solutions when you're solving these equations. For those previous equations that we've done, I haven't gone through that process because I feel like I had to sort of teach a little bit and I didn't want to bog you guys down with checking them every single time. But the problems that we have solved already, those solutions did work. They were valid. I just skipped the checking part. But you're not going to want to skip that checking part, okay?
Mm-hmm.
We're going to get into the next problem here, and you will definitely want to check these solutions to see if they work. Okay, so are you guys ready for the next one?
Yes, sir.
All right. The next one is common log. So log without a base or with an understood or implied base 10, right? Common log of 5x minus 5 is equal to 2. Okay. And I'm going to show the whole paper here. If you guys want me to zoom in, I can do that whenever we get to some stuff. But right now, the first step is the same as the last problem, which is isolate the log expression, whatever this log base b of x is. So log parentheses, if that's by itself, then we're starting off great. Okay. How many logs do I have here? Just one log. Okay. So that means I cannot use the one-to-one property because one-to-one property says I need one-to-one, right? Instead, if I only have one log, I'm just going to convert to exponential form. So I'm going to draw a little arrow over here and say I need to switch this to exponential form. Okay. What is the base of this logarithm?
Mm-hmm. 2,
And
10.
10.
Thank you, right? Because this right here is the common log
Mm-hmm.
with an understood base 10.
No, that's the math. That's the math. That's the
Okay. So we have base 10. What's the exponent?
two.
2. So I'm going to put 10 to the second power is equal to all this junk inside the logarithm. 5x minus 5 goes to the other side of the equation. Questions, comments? Okay, so some students. No, go ahead. That what's up?
Okay, remind me again why there's an understood base of 10?
Because I said so. Um,
Not good enough.
because mathematicians said so. They said whenever you
Okay,
have a log and there's not a, I'm going to zoom in here. Here's the time, right? They said if I write a log and I don't put a base here, there should be a number here, but there's not. Then you need to know that that understood number is 10. This is a
okay,
common log, okay?
okay,
So if you're working out this problem, as soon as you see something that's a log and it doesn't have a base, if you need to, write a 10 there, just to remind yourself that it's a base 10,
okay.
okay?
Makes sense. Okay.
And this is one of those things where like I ranted at length about this earlier. Like mathematicians always do this where they say, oh, this is an understood number here. For logs, you have to remember if you don't see a number there, it's a 10. Okay? Because otherwise, like when we're trying to convert this to exponential form, like how would we know that there's even a 10 in this problem, right? Because we
Right,
didn't see a 10 in this problem at all.
right.
You have to just remember that, or you have to write it down in your note sheet to remind yourself, because it's not going away, right? So we write the base, we put the exponent 2, and then the stuff that was inside the log that gets spit out to the other side of the equation, okay? If we have an exponential expression, 10 to the second power, what we want to do now for our third step is to simplify any exponential expressions. So what is 10 to the second power?
100.
Yeah, so this is just 100 is equal to 5x minus 5. And at the risk of maybe kind of rushing us through this is just a linear equation. So I just need to get the x by itself. So I'm just going to add 5 over to the other side of my equation. I had 5x is equal to 105 now. Then the last step is going to be to divide by 5. And now I have x by itself is equal to, and 105 divided by 5, you guys put that in your calculator, should just be 21.
Mm-hmm.
Okay, so that fourth step, we're just solving the equation. And then we need to check ourselves. But in the interest of
Mm-hmm.
time, I'm going to tell you guys, check this one on your own. It should be good.
It's true.
Okay, yeah, we can, Corey's vouching for us here. Questions, comments, concerns? How are you guys feeling about these equations?
Yeah, you put that.
Corey, you mentioned, I think last week that when you took this class before, your other instructor kind of didn't make the logarithm seem as simple as this. How are you feeling when you're solving these equations?
Oh man, it's easy. I
It's
just see
better
I
than
see
that
it
other
I see it
instructor?
more I see it more clear now. And plus Alex you're gonna have to check the solutions.
Yeah. Yeah, we're
And
definitely gonna have to check the solutions.
yeah, because see, I already know like 21. I just put that 21 into that 5x minus 5 and get 100. So I know the 2 times the 10, it gives me the 100, so it's correct.
Yeah,
And
yeah.
Alex just been having me make me check it as doing the homework.
Yeah, absolutely. And so we want to make sure that we're checking those solutions before you click the check answer on Alex, you need to check it on paper, right? Check it in your
Hmm.
calculator. Because every time you get that red X, I know you guys are dying a little bit on the inside. Okay. Don't put yourself through that trauma. Check on paper, check on your calculator, and then if you're still scared, pop into Math Worlds. Just get one of the tutors to check it, right? Um, but like we should be building some confidence there that we can check these things on our own using the calculator, okay? So that those scary nights when you're working on your homework and there's nobody to hear your screams, that you can get through it. Um, so let's leave this one as it is. We're gonna move on to a little bit more difficult of a problem, of a couple of problems, okay?
Let me
And,
see.
and so these next two are going to be the most scary looking logarithmic
Oh yeah,
equations
yeah,
that
yeah,
we're going to
yeah,
run
yeah, yeah,
into.
yeah. Yeah, I seen this. Yeah.
Okay.
Um,
And so I want to just remind you guys that last class we introduced these log properties. There were about 5 of them, but I've only listed 3 here because these are the sort of major players that you're going to see over and over again. So you saw problems where you had like a single logarithm, and if you were multiplying the inputs x times y on the inside of the log, then we said we're going to take that log and split it up into 2 separate logs, and we're going to put plus, right? Because multiplication or a product gives you an addition problem. Okay. Then we saw some other problems where if I had log base x divided by y, right? Then that division was going to convert itself to subtraction when we separate that into 2 or more logs, right? We also saw this power property that I affectionately call the Yeat theorem, where we take this exponent and sort of move it to the front of our logarithm and multiply it. So sometimes that one comes into play. But what we're going to do is jump into this harder equation here, which has, count them, 1, 2, 3 logarithms. Okay. So I'm going to write this down on paper and we'll work it on the document cam to see how it works out. It looks intimidating and it's a lot of writing. But if you take your time, it's not going to be as bad as it looks. So if you need to right now, take a nice deep breath and try to calm your spirit. Okay, we have log base 2 of x plus log base 2 of x minus 11 equals log base 2 of x minus 35. Minus, minus. Okay, and now we can go ahead and take a look at this problem. Okay, so like I said, we've seen these log equations in 2 flavors up to this point. The ones where we only have one logarithm, we're trying to sort of massage the equation and then convert it to exponential form. Okay, so let's say I had log base b of y equals x. Only one log. What you're trying to do there is convert to exponential form. Okay. Then we had the other ones where we had log base b of a is equal to log base b of capital B, where we had 2 logs. And in that case, we're going to use the 1-to-1 property where we said to drop the logs. Well, in this third case, we can't do either of these things. Okay? So we have to think about this a different way or process this a little bit before we can use one of these 2 properties that we've already learned. Okay? So this is the way you want to handle it. On the left side of my equation, over here, how many logs do I have?
2.
2. And you guys have been practicing karate this whole time without you knowing, right? Because in the previous homework, you said to yourself, if I have 2 logarithms that have the same base, I can combine them into a single log base 2. But now, what do I do with the stuff that was in the parentheses?
Multiply.
I multiply them because I have addition here, right? So that addition tells me I need to take this x and multiply it by this x minus 11. Okay, so don't freak out that I have a bunch of parentheses here. When we're saying multiply, if I have more than one thing here, I'm really distributing, right? So here, in order to combine the logs, we're going to combine with the product property, right? And then we can move on to the next step. Are you guys okay with combining the logs there, like I did?
Oh, okay.
Any questions there about combining those logs into one thing? Okay. So if I combine those into a single log and the product property says we're changing the addition of these two things into multiplication, then we just need to distribute. What is x times x and x times negative 11? So I'm going to rewrite this as log base 2 of x squared minus 11x. Are you guys okay with that? Okay. And this guy over here, I didn't really do anything with it, so I'm just going to bring it down, and now I have this equation where I have log base 2 of x squared minus 11x is equal to log base 2 of x minus 35. Okay? Kind of feels like we haven't done much, but now that I've combined these two logs into one, how many logs do I have in this equation?
2.
2. So that means if I have 2 logs in the equation, I can now drop the logs and use the one-to-one property. Does that make sense?
Yes.
So now I'm just going to drop the log base 2. And now I just have x squared minus 11x is equal to x minus 35, which is what kind of equation here?
Quadratic.
Quadratic. So that means now I have to get this set equal to 0 so that I can get it in standard form and then either use factoring using the AC method or maybe the quadratic formula if you guys are familiar or prefer that. But I'm just going to subtract this x here, and I'm going to add 35 here. Cancel these guys out because it's getting kind of messy now. X squared minus, okay, so this is going to be negative 11 minus 1, which should be negative 12x. Plus 35 is equal to 0. Questions, comments up to this point? Okay. In the interest of time, at the risk of losing some of y'all, all right? I'm going to go into the AC method, but I'm going to do this the fast factoring method. So we're looking at 1 times 35, which is 35. The factors of 35 are 1 and 35, and then 5 and 7. And I need to use 5 and 7, but I'm trying to get a negative 12 here. So those both have to be negative.
Both have to be negative.
Okay. Because this has a coefficient of 1, I'm allowed to take these factors and say, okay, this first set of parentheses has an x minus 5, and the second set of parentheses has an x minus 7. So this is just the quick method because we have that coefficient of 1. If that's not a 1, I can't do the quick method. Okay? Equals 0. So if I set this guy equal to 0, x minus 5, then we get x is equal to positive 5. And if I set this one equal to 0, x minus 7, I get x is equal to positive 7. Okay? Let's zoom out. Now, again, I acknowledge that I did the quick method here, so I'm not going to take any questions about the AC method here. But does anybody have any questions about anything else that happened here? Because we have our 2 solutions, so that means that we should be done, right? as you see me slyly pick up a pen to imply that we're not done, right? So remember, we need to check both solutions here. So I'm going to take this x equals 5 and plug it back into the original equation. It's going to be a lot of writing. I understand that, but we have to do it. So our first check is going to be log base 2 of 5 plus log base 2 of 5 minus 11. And we're going to ask ourselves, does that equal log base 2 of 5 minus 35? So that's going to be for our first solution. Okay. But I want to sort of speed this up a little bit. Okay. So first, remember the domain of logarithms says I can only put positive values or positive input values into my log. So I'm okay to put a 5 here. But if I take a look at the 5 minus 11, can you guys tell me what is 5 minus 11?
-7.
I think it'll be a -6.
Six.
-6, excuse me.
Yeah.
-6.
But in
12
any
minus
case, you should know it's negative. Can I plug a
Mhm.
negative into a logarithm?
No.
No. So right away, this whole thing is undefined, which means it causes an error. I can't evaluate this, right? I can't plug a negative number into this logarithm. And so that kind of tells me right away, this 5 that I tried to plug in here,
I'm good.
since I subtract 11 and get a negative and try to plug that into a log, that cannot be a solution because I need to be able to plug that number all the way into the log. And the same thing would have happened over here. 5 minus 35 would be a -30, which means that this entire logarithm would have been undefined also. So whenever you're getting an error or whenever you're getting undefined, when you're trying to check that solution, as soon as you get that error, throw away that solution. Do not worry about it anymore. Move on with your life. Okay? So if we tried to do the same thing over here, we're going to check x equals 7. So log base 2 of 7 this time, plus log base 2 of 7 minus 11. And we're going to ask ourselves, does that equal log base 2 of 7 minus 35? But do you guys see the issue here?
Mhm.
7 minus 11, what is that?
-4.
It's going to be a negative number. And I can't plug a negative into a logarithm. So right away, that's not going to work. Same thing with this 7 minus 35. That's going to be a negative number too. Right away, that doesn't work either. So that means that this solution doesn't work. So we got two solutions. Neither of them worked. So that means in Alex, you're going to select the button that has the empty set. Or you're going to click the button that says no solution. I forget which one it gives you. I think it gives you the button that says no solution. Okay. Now, I only have 2 minutes left, and I don't want to keep you guys over, but I do want to show you guys that I ran through this problem here in the PowerPoint, right? We solved the quadratic equation, got our two solutions, 7 and 5, not in the exact same order, but we got the same things. And then we checked those solutions. Okay. And I don't think that I showed how to check those solutions in the PowerPoint. Okay. So just make sure that you're doing that. Then, if you review the PowerPoint on your own or want to hang out after I dismiss here in a few minutes, there is one more problem that I go through in the PowerPoint. So please use that as additional practice, but watch out because this has two logarithms on one side of the equation,
Mhm.
but we don't have a logarithm on the other side. Also, what's different about this problem is that we have a minus sign between those logs. So right away, that's telling me I need to combine these logs using the quotient property. So right now I'm just hinting at how to approach this kind of a problem. Be very careful when you're looking at these equations to ask yourself, first, how many logs are there? If you have multiple logs on one side of the equation, can I combine them? And if I can combine them, do I use the product property or do I use the quotient property? Okay, and then go from there. Okay, I go through this problem in the PowerPoint, so you can check yourself to see how to solve this problem. But we don't have enough time to go through it in today's lecture, okay? So make sure that you're getting into the homework and you're practicing these problems. And then the last thing that I wanted to say here is just to remind you, for those of you that joined our Zoom session a little bit late, tomorrow we're not going to be meeting for class at Zoom, okay? Because tomorrow would be the day that we usually work on the review for the test, but I want to do things a little bit differently. So if you go to the Canvas announcement that has now been published, it got published at 8 while we were doing our class. Tomorrow is going to be an independent review day. We're not going to meet, but what I want you guys to do is take the time to work on the review for test 4, and if you have more time, the practice test for test 4. Okay? Because test 4 is going to be due at the end of the week on Sunday. So you have plenty of time to go to Math World, get some assistance from either me, Pete, Gilly, or any of the other assemblage of tutors that we have there. So just make sure that tomorrow evening you don't log into Zoom unless you're Zooming with the math tutors, okay? And then if you are ready to take the test, I put all of the information for test 4 here, including the password. So for those of you that are locked and loaded and ready to go, you can go ahead and try that, okay? We will resume class on Wednesday, and we'll start working on the last bit of material that we'll have to cover for the semester so that we can then turn our attention to focusing on getting ready for the final exam. Okay? So that's all I have for you guys today. If you want to hang out with me, ask me some questions here in the next few minutes, you totally can, but class is dismissed. I'll see you guys on Wednesday.